It's very nice to virtually meet you in those pandemic circumstances. So in this talk, I would like to talk about an introduction to reinforcement learning. And rather than going like into very specific details about like different algorithms, like I will try to give a fairly broad overview of what the field is about. So in order to talk about like reinforcement learning, at first we have to talk about supervised learning. And to start with, I will just reintroduce what artificial neural networks are. So artificial neural networks are connectivist models of computation where activations from previous levels of layers of a neural network are propagated to other layers of a neural network by combining previous activations, multiplying them with weights, summing them together, and applying some sort of a nonlinear function in between. And like very similarly, once activations in the second layer are calculated, then activations in the third layer can be calculated. And typically, like neural networks may consist of many layers, and the key here are linear operations in between layers and non-linearities. So for example, like what is our goal when we are training an artificial neural network? So for example, like imagine like if our goal was image classification problem, when we wanted to classify images of cats and to distinguish them from images of dogs. So one can take an image, rasterize it, and take every single, split the image into many different pixels, read off image intensities, and treat those intensities as inputs to the first layer of a neural network. Then, during the training process, we would apply a linear operations by mapping inputs in the first layer to the second layer, then apply nonlinearities, then again apply linear operations on nonlinearities, and the neural network would tell what it thinks, whether it's a cat or a dog. And of course, like initially, it would guess the answers that are most likely incorrect. So, so the key here during the training process, the key here is to alter all those weights little by little, so that like the next time when the same image is produced as an input, the neural network would be more likely to say that, for example, this is a cat, this is the image of a cat. And like during the, basically during the training process, like every single time we updated those weights, the solution would be more like the answer for this particular instance would hopefully be more and more correct. And like the goal is, of course, generalization. Once we finish training, when a well-trained neural network should be able to distinguish cats with dogs by taking unseen inputs and correctly attributing labels to them. So for most practical like circumstances, like this is what the field of supervised learning is about. We have inputs, we want to map them to known outputs. And the answer whether something is right or wrong is typically known instantaneously. Now, reinforcement learning is a slightly different paradigm. So instead of us guessing or classifying whether an image shows a cat or a dog, and we know the answer immediately, now we are in real world, many decisions and rewards for those decisions are delayed. So for example, if someone decides to study computer science at the university, maybe like initially one doesn't get an immediate reward for studying computer science. Like one has to graduate from computer science, find a job and do something interesting, and then like gratification and rewards would follow. So very similarly, like very often in life, actions have delayed consequences. And initially, whether it is not well known whether a particular action was a good choice or a bad choice. And this makes like reinforcement learning a fairly complicated framework to train, because unlike previously when a network could be penalized for a bad decision, now it's not clear how good or bad the decision is. Now, to start with, talking about like deep reinforcement learning, one ideally should look into simpler problems first and remember certain tasks from maybe computer science competitions that I believe many of our viewers have encountered previously. So imagine that the goal of the squirrel, which is shown on the screen, is to collect nuts. And a squirrel can go either left or up, but cannot go right or down, making the problem acyclic. And one of the ways to solve this problem is dynamic programming. So dynamic programming is the process when we, for each square, starting from the end of a game, we try to calculate the score, the maximal score obtainable if one starts playing this game from a particular square, and then continuing onwards. So as the last nut is on the top left corner of the screen, like obviously the score is 1. Then similarly, when we are considering this square, we see that there is no nut at this particular square. There is one, but it's possible to get one score if we go left. So then we attribute also the score of 1. Now, more interesting things happen if we encounter positions, for example, where a particular where another nut is. So, for example, here we know if we start from this score, we would be able to collect this nut, and then in the future we would be able to still like get one other nut like in the future. And once we fill when we, for example, fill in this particular entry, so we consider what happens if we go left up, and in that case we collect one nut. And what happens if we go left? In that case, like we would be able to collect another nut, and then by going upwards we would be able to collect the second one. So like this is dynamic programming. Like there is nothing particularly complicated but just by filling a table and using a particular rule, we can calculate what an optimal policy is and how many nuts we would be able to collect. So this is like the standard curriculum in computer science competitions. Now, value iteration is a slightly more interesting problem. So imagine now that instead of only being able to go up and down, we can go anywhere, like up, left, right, and bottom. And as we can close cycles, dynamic programming no longer works. But imagine like the following slightly different problem. Let's suppose that there is a squirrel that wants to catch a nut. It gets -1 score for every move it makes, and there is a slippery slope. So if a squirrel walks along the slope, with a probability of 1, it can slide downwards. With a probability of 0.3, it can slide downwards here, and with a probability of 0.1, it can slide downwards, like at the other side of the cliff. And the key here is, of course, to find the path that would maximize her reward or minimize like negative rewards. And in this particular case, like we know the dynamics of the world, and we are able to tabulate every single possible position of the world in computer's memory. And we know all transitions. So we know what happens if we go right from a particular square. And in that case, like in those circumstances, we can use value iteration. So value iteration is another algorithm, but unlike dynamic programming, it repeats the same computation for every square, not once, but many, many, many times until convergence. So for example, if we, and for each square, it tries to estimate Q values. And a Q value is the following. Is a number answering the following question. If, let's say, I start from this square, and if I turn right, how many points in expectation I would get? And if 1A is able to calculate such function for every square in the game, so by always picking the action that would lead to the most amount of points in expectation, what would be maximizing the total reward? And then one would be able to find the path that catches the nut most quickly. So for example, like this is how value iteration would work for this particular square and this particular action to go right. So value iteration would say, algorithm would say that when you estimate for a Q value, so for an action value, if we are here and turn right, is 0.1, so the probability of slipping down from a cliff, icy cliff, times the maximal value we can get if we slide down, plus 0.9, so the probability of not sliding down from the cliff, times the maximal value we can get starting from this square, and plus the immediate reward in between those two in between of those two states, but like in this our example, this is just 0. And if we happen to repeat the same operation many times a game for every single square on in the game, like we would be able to maximize the reward. No, okay, fair enough. Like, so why not just use a value iteration everywhere? Well, it turns out it has problems because it requires us to know the dynamics of the world precisely. And in some cases, like maybe this is impossible. Like maybe we need to act by trial and error and observe what the dynamics of the world is. So Q-learning is a slightly different algorithm. So instead of relying on us, so it requires sampling experiences from the environment. So a squirrel would learn to reach the nut by trying many different trajectories. We would sample many different trajectories. For every time, every time we were in some state A, we would take, let's say, action like right. We would observe what the next state is empirically. And let's say in this particular example, we slid down with a probability of 0.1. And it would always execute this update rule that basically the new Q value estimate for action right in this particular square is equal to the old one averaged with a new value of what happens if we slide down, and lambda here is the learning rate. So lambda defines how how quickly we learn from experiences. And the smaller the lambda is, the longer the learning will take, but like the more stable it would be. And of course, like if a squirrel tries many trajectories, every single time it observes, like it visits states, it updates Q values for that state and action in this using this particular formula. After many trials, the squirrel eventually would learn how to reach the nut most quickly. So okay, so far so good. Like, why not use Q-learning all the time? Well, it turns out that it may not be possible for problems in real world may be so large that it may be impossible for us to tabulate every single experience like in our memory, in computer's memory. And it may be impractical to visit every single possible like position. Imagine like if you were walking in Vilnius, like it's hardly possible in a reasonable time to visit every particular position in the city. One may need to generalize. So ideally, what we want to do, we would like the squirrel to be able to try some trajectories. And in dark blue here, I marked squares that are non-visited. And we would like to develop such an algorithm that by visiting some squares and seeing that like, okay, I can slide down here and here it's non-slippery on the top, that somehow the algorithm would generalize and interpolate for the states it had not seen before. By interpolating, we hope that it would be able to solve some practical problems. Well, it kind of makes sense because in life, like people, a person doesn't have to have tried every single street in Vilnius or every particular pavement block of a pavement to be able to generalize that. For example, if I'm walking on the right side of the pavement and on the left side of the pavement, that my arrival time should be approximately the same or maybe like differ by a very small amount of time. So what we want to do in this particular case with deep Q-learning, instead of having a table that we are filling for every particular position in the game, we would like to train a neural network that would tell us, that would be able to answer the question. At this particular state, if I take action A, what is the expected amount of points I'm going to get in the future? And when I'm acting, I would be acting in the following way. For every particular state, I would evaluate action values for all actions and just pick the one which promises me to give me the best result. And then like an optimal policy would be found. And of course, the question remains how we should train that Q function. So deep Q learning is like an algorithm that is able to train such Q functions. So like we have a huge game, remember, we can't store all states in the table. And we use neural network as a functional approximator. So typically, like deep Q learning, when it is trained on Atari, uses the last 4 frames of a game as an input. Then, similarly, like in those examples of cats and dogs, those 4 frames go into a deep Q network, and a deep Q network produces outputs, which would eventually be completely wrong, but as training progresses, would become more and more accurate. And the network will try to say, if I'm in this position and turn left, what will happen? If I trend right, what would be the expected reward? And so on and so on and so on. And the algorithm like works similarly like I described before. So we play a game and put experiences into replay buffer, like the squirrel which was collecting nuts. Random transitions are sampled from the replay memory, and a Bellman rule is applied. And the Bellman rule is something like something not very complicated. What effectively, like this fairly complicatedly looking maths tells us that every single time we observe at some transition from one state to another, and we get some reward R, we estimate the new version of the Q of an action value in the old state as the reward plus the maximal Q value in the next state as given by the same neural network, more or less. And of course, like in a deep learning terminology, like we calculate the delta, we calculate gradients of a gradient of the neural network parameterizing the Q function with respect to all of its parameters. And then we move all of those parameters a little bit towards the direction that would make the prediction more consistent next time. So it's conceptually not very complicated, but in practice it works quite well. And I can show you like a few, oops, like the video is unavailable. Okay, it's a little bit of a problem. So we will have to use our imagination. Oh, no, never mind. So we will have to use our imagination. So okay, so effectively, like the agent is able to learn. The agent is able to learn to play both Breakout, like and many other like Atari games simultaneously. Okay. Now there are different types of reinforcement learning algorithms. So there are value-based algorithms and policy-based methods. So value-based algorithms are the ones that I've described previously. So it is the algorithm of deep Q learning is one of those value-based algorithms. And the idea here is to train a Q function telling us how much scores we would get in expectation if at state S we take action A and thereafter we follow an optimal policy. However, there are other algorithms like policy gradient-based algorithms. And policy gradient-based algorithms, instead of trying to evaluate action values directly, they try to produce a probability, they try to produce a policy without explicitly evaluating it. So we try to find an optimal policy, we try to produce a neural network that for each state gives a probability with which we should take a particular action. Then, of course, like reinforcement learning algorithms are divided into two categories based whether we are on policy or whether we are off policy methods. Off policy methods typically allow us to be able to learn an optimal policy without even playing the optimal policy. So it allows us to learn about an optimal policy by looking to the experiences generating by suboptimal policies. However, on policy methods, it can only improve policies that we are playing or we are acting upon. Well, in practice, like off policy methods are very important because imagine if one was building some sort of a recommendation system using reinforcement learning, one may want to do some sort of a policy improvement without like affecting behavior first. And also, based on whether the algorithms you use planning, there are also different sorts of reinforcement learning algorithms in practice. So the ones which use no explicit planning, so we just like estimate action values, as I described previously. The ones which use both, uses both a learned policy and does explicit planning by running Monte-Carlo tree search or minimax algorithms. So this is what AlphaGo would do, or many chess programs would do. Or there is another option, which is but the first the planning option typically requires having access to a high quality simulator. And then the last option is, instead of using a simulator tried to learn the dynamics of the environment, and if you don't have access to the real simulator, and use planning on top of it. And like usually, like the last problem is the most complicated problem to be resolved. Now, okay, so there is another like YouTube video that I can try to show. So this time, those are asynchronous methods of this time it is not a Q-learning, but a policy gradient method trying to learn, and not even trying to learn, but playing, I think, like the game of torques. And you can see like it is able to control the car like fairly well. Now there are also like different training regimes that like I would like to mention. So in real world, like, we may have to do single episode learning within a single episode. So an example of such problem would be, imagine a delivery robot going onto a street trying to deliver a parcel. Like you cannot like you can only crash so many robots. Then there is the training regime of multiple episodes when we start from the beginning, or each episode, or multiple parallel episodes. And typically most of reinforcement learning research operate in this domain. And even some robotics research operate in this domain when we try to pre-train policies on simulators and then fine-tune policies using real robots in real life. And the last domain, the training regime, is multiple episodes with arbitrary starts and using tree search that I mentioned before. And an example of such regime would be AlphaGo, AlphaZero, and many discrete optimization tasks when we have simulators available. So in other words, like even when we are talking about reinforcement learning, like there are many different formulations of the problem, and depending on the formulation and practical constraints of the problem, there are different algorithms that would be operating in those domains. Now, another problem that I would like to talk about like is exploration, because exploration is a fundamentally important problem for reinforcement learning. Because before we explore the world, we don't even know what to learn about the world. It is not a supervised learning task when we get served images of cats and dogs, and like we know the domain on which we have to produce estimates. So imagine like we are in Vilnius, we start somewhere close to Vilnius University, and we need to, we want to reach a goal close to Misionierių Gardens. So there are like different ways to accomplish that. Like the first way of trying to find Misionierių Gardens is to just walk randomly. Like choose a random direction, walk until the next intersection, then choose another random direction, and then continue walking like that. And in reinforcement learning, this is called Epsilon-greedy exploration. But one can imagine that one cannot travel particularly far if one is following this strategy, because effectively one is running a Brownian motion. So then like people thought like, is it possible to do somehow better? And like we know from discrete problems and from computer science competitions and classical computer science, that like there are other algorithms that are able to find the decisionation more quickly. So the first algorithm like is a depth first search. So instead of just like executing a Brownian motion, like we would just run a depth first search zigzagging through the streets of Vilnius until we find Misionierių Gardens. Fair enough, but this depth first search is typically not a very effective algorithm, because one may even end up in the situation when one goes to Kaunas first and then like comes back to Vilnius and then finds Misionierių Gardens. So it like arguably like it's a bit suboptimal. But there are other algorithms, and the other algorithm is breadth first search. So effectively, like the idea would be trying to zigzag, if you were a robot, trying to zigzag streets in some tight pattern by expanding radius gradually until like we find the destination. Those are, of course, like classical search and exploration algorithms, but we can still build some intuition for reinforcement learning. And indeed, like in practice, of course, maybe like it's easy to illustrate the concept on a map of Vilnius, which is nice and two-dimensional. However, in practice, state spaces that we have to deal with are very high-dimensional, because imagine if a robot was exploring Vilnius, who told the robot that X and Y coordinate is the state? maybe like its x and y coordinate and a velocity, the tuple is a state that the robot should take care about, because if, let's say, a robot exceeds the speed or the limit of speed while exploring, it can get busted by the police. So in that case, like even velocity could affect the final outcome of exploration problem. Now, also counting is also very difficult. Like in a discrete problem, when a squirrel is collecting nuts, it's possible to define and understand very easily when we end up in the same state. But what should we do when we are always observe a world that is changing and we can never step exactly in the same river twice? And also we should do something when the world has stochastic dynamics. For example, that can be caused by maybe like wind or by other agents within the environment or the traffic light systems and many, many other problems. So I would like to talk a little bit about typical exploration algorithms used within the area of reinforcement learning. So usually, like most of the algorithms in deep Q learning works in a very simple way. So once in a while, let's say with a probability of 5%, like it just always tries a random action and sees what happens. And actually, it turns out like this is a very ineffective, but like algorithm in terms of data efficiency. But this algorithm works to some extent on many problems that you can try it on. However, there are other arguably more interesting and sophisticated algorithms to be tried for exploration. So like one of the ideas is the following. So if, let's say, we are walking through the streets of Vilnius and we somehow detect that we had been in this place or in approximately the same place multiple times already, maybe we should stop going here and start concentrating on somewhere else. And one such algorithm is called, was produced in the paper called Unifying count-based exploration with intrinsic motivation. And the idea is the following. Maybe somehow we have to use a neural network trying to estimate density of states that we had visited. And by density of states, I mean maybe like try to estimate. So the first thing one can think about how this, what should we do when estimating density of states? One may think that maybe like we should have a neural network like just trying to predict the next state, and if what the next state is, if we turn, let's say, right at any given position, and if we mispredict, we should reward ourselves and use the same reinforcement learning framework and just go to places that we cannot predict. Okay, fair enough, like you can try running this algorithm, but the problem is that if you run this algorithm for a very long, you may end up in the situation when an agent just approaches a TV, tunes into a noisy channel and observes all the unpredictability and entropy from the environment. So then people thought, okay, like if just going to places that we cannot predict is not good enough because the agents may be attracted to just simple noise, maybe we should find places and reward ourselves for going to places which were unpredictable, but after observing the transition, we became slightly more predictable. So basically, like if by observing a transition, we were able to understand something better in our past. So imagine the following problem. If we are walking through the city and see the first red car, then we would reward ourselves. Then we observe a second red car and it helps us to better compress the observation of the first red car, so we would reward ourselves again. Maybe like we would reward after seeing the third and the fourth red car, but like after the 10th one, new observations of red cars would not produce any more information about previous observations, and we would stop rewarding ourselves. And effectively, like the paper of Unifying count-based exploration with intrinsic motivation tried to do this thing by using generative models and trying to estimate something which we call prediction gains. So instead of rewarding ourselves for observing states hard to predict, we would reward ourselves for states that were maybe hard to predict, but help to predict something in the past. And eventually, once the prediction gain is exhausted, the agent would stop going to that particular place. Now, another like algorithm, which is maybe slightly simpler, is exploration by random network distillation. And actually, it's also like a fairly neat idea, maybe slightly related to the problem that I mentioned before. So if one neural network is initialized randomly, and the second neural network is just being trained to predict what the first neural network would predict for a given observation. And the idea is the following, that if we visit a particular state very, very often, then the second neural network would distill predictions of the first completely randomly initialized neural network, and the discrepancy would become 0, and then the agent should stop being rewarded for reaching that particular position. And also, like, there are slightly more sophisticated algorithms. Like, the problem with a few previous algorithms is the following. So imagine, like, if this particular state, let's say this particular state had a high prediction gain. Reinforcement learning algorithms are usually very, very slow already to converge on stationary rewards. And here we are producing non-stationary rewards. So imagine, like, this particular state has a high prediction gain. So a reinforcement learning algorithm would learn to approach this state until it would start exhausting the prediction gain, and it will no longer be interesting. And it will start giving prediction gain of 0. However, as the reinforcement learning algorithms are slow, it would take a very long time to backpropagate zeros back to the initial position. And for a very long time, the agent would still keep going and keep going and keep going to that position which is already exhausted. And even worse, at some point, the agent would start differing, because as rewards get backpropagated in time very slowly, there would be likely a position where the agent believes that by going right here, it would still get a reward, then would go right, and will figure out very quickly that no, there is no reward to be found, let's go left. And then the value function would be evaluated again and would say, like, well, listen, if you go right, like, you will get a reward, and agents would start differing and wasting resources. So, like, this is another fairly cool algorithm that was introduced partially to alleviate this problem. So instead of using a random network distillation that produces a very slow signal of coverage, it also produces and uses an episodic memory and uses an embedding network to somehow embed states. Actually, it doesn't really matter exactly how those states are embedded into some small dimensional space. And the idea is the following. It memorizes all states seen in this episode. And if every single time it observes a new state, it compares state embeddings to previously memorized embeddings from within the same episode. And if a new state was found in this episode, then a positive reward would be given. But if it starts seeing that the agent is wasting time by going back and forth and getting back to the same states within the episode, the rewards would be the rewards would be 0, and effectively multiplicative modulation would produce a 0 reward. So basically, like, this is a method this is the attempt to increase both intra-episode and intra-episode diversity of states that the agent visits. And to this day, it's one of the most successful algorithms on Atari. And of course, like, the implicit assumption, like, behind this algorithm, like behind many, many other algorithms, is that states are fairly low dimensional, because to this day, we don't know how to explore very high dimensional spaces effectively, and most Atari games at the end of the day are fairly low dimensional. Usually go left or right or forward or backwards, and then continue going in along those directions. So basically, like, I gave an overview of, like, a few algorithms. And of course, like, there are many families of algorithms that, like, do other things. So for example, we somehow try to partition spaces and dedicate resources towards exploring within within this subspace of, again, that subspace, that and that subspace. So maybe, like, the goal is, of course, try to somehow emulate as much breadth first search rather than depth first search as much as we can. And of course, like, a good exploration strategy, like, it also depends on a good representation that we learn, because it is very important, like, for a good strategy to learn that certain areas or certain variability within observations doesn't matter, while some other axis of variability do matter. So, like, those were, like, exploration algorithms. Now I will talk about exploration a little bit. Sorry, not exploration, but applications a little bit. Like, exploration is already covered. So in order to apply real reinforcement learning in real world, typically one has to solve sim to real problem. Reinforcement learning algorithms, and especially deep reinforcement learning algorithms, are very, very, very inefficient. And typically what people do, they train reinforcement learning algorithms on simulators and then try to transfer the experiences into real domains. And I will cover a few applications. So like one of the applications of reinforcement learning algorithm would be learning bandit algorithm. So bandit is the algorithm, bandit is a problem where typically people encounter when dealing with many problems in life. And one of those problems would be A/B testing. So typically what happens for a particular parameterization of possible distributions of rewards when we pull the left hand of a bandit, and a bandit like can also be fought as a slot machine in a casino. And imagine like a casino player wants to determine which slot gives the maximal rewards. And of course, like the casino player initially has some beliefs about those rewards. Tries pulling, like depending on the beliefs, there are different algorithms how in what order like bandit hands should be pulled. And every single time a bandit hand is pulled, a reward is obtained. The reward, this uncertainty about the reward distribution would be shrank. And even about 10 years ago, for every particular parameterization of a problem, whether we believe that rewards come from beta distribution or some other distribution, there was almost a PhD thesis that was dedicated in finding a particular strategy how you should pull those bandit arms until you decide which bandit arm produces the best results. And like in practice, that would be like related to A/B testing. Like you're presenting maybe 2 website designs to customers, but like you want to make as the least amount of customers dissatisfied, and maybe like terminate the experiment early as you can, like in case if the success is low. And the key in here behind the algorithm called learning to reinforcement learn was the following. So instead of spending a PhD thesis for a particular parameterization of a problem, let's generate a lot of bandit problems. Ask the reinforcement learning agent to pull those hands. And depending after a certain budget of pulls that we can afford, reward the agent whether it knows which hand was the best or which hand was the worst. And then this algorithm is able to learn an optimal pulling strategy for a particular parameterization of a problem reasonably quickly, like without spending a PhD thesis on it. So I personally found this application to be very cool. The second application that was often talked about, like reinforcement learning can help to reduce data center and cooling costs at Google. And also reinforcement learning can learn to control balloons. And this is a fairly new paper by Google Brain, by Belmer et al., published in Nature. And the idea is the following. Google had the project Loon, where the aim of the balloons was to hover over a particular place and provide connectivity. And depending on, but the balloon can only do 2 things: go up and go down. And depending on where the winds are blowing in different heights in the atmosphere, by going up and down, the balloon can explore winds. And then by choosing optimal winds, it can learn to hover over a particular area, which I think like is 50 kilometers around the base station. And typically, like most of this work was done by just having handcrafted controllers. But it turns out that the reinforcement learning agent was able to beat all of those handcrafted controllers and keep the balloon over the dedicated area with a maximal precision. And of course, like the idea to solving this problem was having a good weather simulator for a particular place, using reinforcement learning to train strategies using deep Q network, this more or less a very similar algorithm to the one that was playing Atari, and to reward the algorithm for whenever it keeps the balloon within 50 kilometers from the base station, and reward less if it flies further away. And it turns out that the agent that learned on the simulator was able to control real balloons. And the key here behind the behavior of the agent is still the problem of exploration versus exploitation. The agent, to some extent, needs to move around up and down to explore wind directions. So basically needs to explore, but also it needs to exploit in order by choosing optimal heights so that like it would be able to hover over a particular place. The third application like of reinforcement learning that is super cool is chip design, because I'm not an expert of chip design, but the way how I understand the problem is that once the logic of a chip is designed, and we know that we have a bunch of components that have to be physically located on a two-dimensional chip somehow, we would like to arrange those parts in a way that total wiring distance would be minimized, because like wiring both costs the money, and also wiring introduces latency, wiring produces heat, and it is a very highly non-trivial problem to produce an arrangement of parts on a chip subject to the constraints that the chip designer has. And the idea is, of course, like that a neural network was trained by producing a very diverse set of possible chips that have to be placed on a two-dimensional board. The agent was then asked to choose a position of each chip one by one by one by one. And after all the chips were placed, if the configuration was feasible, then a proxy for a reward was evaluated, and the agent was fed into, and the reward was fed back into the reinforcement learning system. And then at the end of the day, the reinforcement learning system was able to generalize to position components like of other previously unseen arbitrary sizes. I think like this is like a very cool application of reinforcement learning yet again. And like this is another work, like this is not from DeepMind nor Google, this is from OpenAI. And this is an example of reinforcement learning when it was used in robotics. And reinforcement learning algorithms were trained in simulation to do dexterous manipulation of objects. Like a robot hand was trained to manipulate a cube in its hand. And the experience, like as the simulation produces experiences which were diverse enough and algorithms were good enough, the experiences were able to transfer into the real world as well. So I think like this is a cool application of reinforcement learning. Like I personally, the more time I spend, I personally like more and more care about applications, and I think like that the area of reinforcement learning like has a lot to offer. Another application of reinforcement learning is improving machine translation, because typically machine translation models are trained to minimize cross entropy and predict each word at one token or word at a time. So let's say an input is a French sentence, the output is an English sentence. However, once you produce, if you train networks like that, instead of producing the maximally likely or the best outcome, one is producing a typical outcome. And typically, like and then there is another problem that by choosing a word which is very likely at position 1 may end up being in a situation where one has to choose between very unlikely words in a position 2. And typically, like either in machine translation, people use either a greedy search that produces slightly suboptimal results, or beam search that tries to maintain a bunch of beams with possible word positions like at every choice. Imagine like initially it would be maintaining the option to choose A at this position and C at this position, but after seeing what other likelihoods are for token in position 2, it would be rejecting previously seen position C, and then would continue, all those beams would continue along this those two lines. Or it is possible to use a Monte-Carlo tree search, an algorithm very similar to the one used in AlphaGo, and to run a tree search to produce for the most likely outcomes. Or ideally, or also not necessarily produce the most likely outcomes, but also produce outcomes that measure some other measure that we are interested in, as opposed to cross entropy that was used to train it. So effectively, like Monte-Carlo tree search can be used to consider a whole variation of possible translations and like in a tree-like manner, and then pick the best one. So yeah, I think like I mentioned like most of those things before. And like there is the last topic, which is called multi-agent reinforcement learning. So previously we talked about like the problem of a single player in the initial examples, when everything is seen, like, and why a particular player knows exactly when one is. So this is the setting of Atari, a squirrel connected nuts, and so on. However, like in robotics and many other problems, we don't have MDPs, Markov decision processes, but we have partially observable Markov decision processes. So for example, in robotics, the agent, due to the position of the camera and stochasticity in the environment, may not be able to see where its hand is at any given point. Let's see, if my hand was behind my back, like I can no longer see where my fingers are. So an example of such problem would be robotics. Then we have two-player problems, which are fully observable, like chess and Go. And we have two-player problems that are partially observable, and an example would be a two-player poker. Then we have three-player problems, which are fully observable. An example of them would be Risk. And we have problems that are multiplayer problems and partially observable. An example would be multiplayer poker with more than two players. And as a rule of thumb, actually, to this day, we as a community, we don't know what to do with three-player problems and beyond. But we have a fairly good understanding how to deal with two-player problems. And the Go is an example of such problem, which is fully observable. And it has two players, and like it was one of the initial achievements of DeepMind that made the company like somewhat famous, I would say. So unlike chess, which has a reasonable numbers of choices for every move, Go has a very, very high number of choices for every move, making running a normal tree search, an exhaustive tree search, not very feasible. And instead of running a tree search, the Go project, it does run a tree search, but it needs to do very aggressive pruning because not all possibilities can be checked. And Go used convolutional neural networks, both for a value function that was trained using reinforcement learning and for policy function as well. And instead of running an exhaustive search, it was using Monte-Carlo tree search guided by the policy and value networks. And this allowed to do a very effective pruning of the tree search so that the gameplay would become feasible. And as I mentioned before, like very similar technologies using Monte-Carlo tree search, actually these days can be applied in text generation problem and machine translation problems. So basically, like the technology is more practical than just for a single game. And then there are, as I mentioned before, imperfect information games. So for example, imagine like we have two players. Player one has to choose whether to go left and right, and player two cannot observe whether player one chose to go left and right. Unlike in Go and unlike in chess, it is very hard to know for player two how it should best respond, because player one may be bluffing and the optimal strategy may not be a deterministic strategy, but it may be like a stochastic strategy. And to illustrate this the problem of imperfect information, one can like very easily imagine a fog of war that one sees in many computer games. So imagine like if this is the first squirrel that has to make a move, and this is the second squirrel that can see only one step ahead. As long as the first squirrel doesn't make a move which goes into, as long as the first squirrel has to make a move which is either left, up, down, or right, the second squirrel is not able to know where the first squirrel is, and as we are competing for this nut, the second squirrel should be able to handle many different actions of the first squirrel and also bluffing strategies. And imperfect information games, especially when we are zero-sum, we are trying to find Nash equilibria as opposed to a deterministic best response strategy. And like finding Nash equilibria is fairly important. So an example of such domain is StarCraft, and AlphaStar was an algorithm used by DeepMind to learn to play StarCraft. So unlike Go, the problem is very complicated, also much more complicated in some senses because it's partially observable, you can't see what the opponent is doing. Your opponent may be bluffing, and you would have to bluff in order to prevent your opponent from exploiting you. And also, like, another project was Capture the Flag, where teams, where neural networks were able to were trained to play the game of Capture the Flag, and which is also very highly partially observable because it's a three-dimensional game, and you can only see like what is in front of you. And typically, like, it sounds like multi-agent problems may not have like a lot of applications, but it turns out that we have, and applications are in auction design, in energy systems, especially smart grids, when one is trying to find policies that people would respond to in desirable ways, or also like in transport networks. So thank you very much for listening. Like, it's been a pleasure presenting to you. I'm looking forward to any questions if you have any.
Thank you, Audrūnas. You're right on time, and we have a few questions. So let's start with the question from Dmitry.
Okay.
He's asking, are you familiar with intersections between reinforcement learning and causal inference or experimental design? And if you have any pointers regarding these intersections?
No, I actually, like, I do not like have like so much experience myself like within that intersection, so like I'm not able to answer this question properly. The issue, like, so like this is my answer, like, my apologies.
All right, it's I think okay. We have a few more questions. Another one by Dmitry. Could you potentially elaborate on how reinforcement learning is used in AlphaFold?
I'm actually like okay, like I cannot like answer this question because I'm not so familiar with the work of AlphaFold myself. Like, and to the level that I'm familiar, like I do, like I don't want to speculate nor like mislead you by an accident. So like my apologies, like I cannot answer this question as well.
Okay, let's we still have like a few questions, so I think it's okay. Maybe you know you could like Dmitry could ask you the questions on Slack, and
oh, yes,
you could answer them on Slack. All right, perfect. Let's move to the next one. Robin is asking, the reward design seems to be very hard and require human expert knowledge in the real world example, like the balloons. What to do if we don't really know how to design the reward?
So like, okay, like to some extent, like we still need to be able to define like what the success is in some ways. Like, because like if you cannot define what the success is, like basically like this is game over. Actually, like there is a stream of research within reinforcement learning, which is called no reward learning. So basically, like the idea is how much can you learn about the environment if you don't know what you're doing? So to some extent, like maybe like those are people on Earth, like people ask philosophical questions, what is the meaning of life and those kinds of things. However, like the third approach, if you have some vague idea of what the reward is, at least you can attribute like +1 to some states and 0 to the others. Like you can maybe like try to evolve like your reward functions, but like generally speaking, like you still must know what you want from your robot, because you don't want the robot to impose your will on you.
All right, yeah, great answer. Yeah, so in all cases, I guess it's important to at least know what you want the agent to do.
Exactly.
Let's move on. Up is asking a question. What are your thoughts on improving the data efficiency of reinforcement learning algorithms? Also, is there a possibility that the use of a specific exploration strategy might bias the agent towards a particular solution?
Okay, answering from the easiest part, yes, the use of a particular exploration strategy would most likely bias the agent to a particular solution in those circumstances when the optimal solution is not found. Because you see, like ideally, if everything works correctly, like the agent is in theory supposed to find an optimal solution. However, there may be some solutions that share the same expected value. So in that case, like, of course, the strategy would bias. And the second thing is, it may not find that optimal strategy. And yes, of course, it would bias, because like a bad exploration strategy may just give rewards of 0. Now, this is the second part of the question. I forgot the first part of the question.
So I'll repeat the first part.
Okay.
What are your thoughts on improving the data efficiency of reinforcement learning algorithms?
I think like it's very important for many domains when you don't have a simulator. So for example, a robot in real world. However, or like a recommender system being updated, or A/B testing, or anything like that done with real people, like with real clients. However, and it is very important to update data efficiency. In my view, in the community, there is a little bit of a blind spot, like at this particular moment, that like people don't care about data efficiency as much maybe as I do. However, there are also some other problems why it really doesn't matter. So an example of that would be a bridge building simulator. Imagine like you want to design an optimal bridge and you know how to simulate a falling bridge. However, while you can simulate the bridge, you don't know how to design a bridge. And in that case, like data efficiency doesn't matter, then exploration is very important, because so like that would be like one of the examples. Or even like in a very general case, like maybe like protein folding problem. Like if we knew how to explore the space, high-dimensional space very, very efficiently, like maybe the protein folding problem would be even easier. But like it's also partially an exploration problem.
Yeah, all right, great answer. Let's move to the next question. Do you have any suggestions how to handle non-stationary environments?
So like it depends on an algorithm. Usually on policy algorithms, from my experience, handle non-stationary environments better than off-policy algorithms. So for example, like maybe A3C would have less problems with non-stationary environments than DQN. So like typically like there are tricks, like for example, like bootstrap less often and use the actual return as much as you can, because like every single time you like if you bootstrap at every state, you are decaying your now invalid rewards very slowly. If you're using full returns with importance weights without any bootstrapping, then you're not almost suffering from non-stationarity as much. But like, so basically like there are a few other things. However, like maybe there are algorithms in between. Like you can think of like running statistical tests, trying to determine when, let's say, your data in your replay memory becomes irrelevant. But generally speaking, like I don't think that like any very clear answers have been obtained, and typically reinforcement learning operates the best when the rewards are stationary. But this is a very good question. It's a very open problem.
Yeah, and maybe to add a little bit to the answer, yesterday Razwan covered quite a bit on the non-stationary learning in his talk about continual learning. Mm-hmm. So I think it will be worth to check out for the person asking the question. Mm-hmm. Let's move to the next one. So James is asking, what is the most popular / general approach to researching reinforcement learning? Is it more computational, iterative method, or mathematical modeling?
Okay, like it's very hard. Like it's almost a philosophical question. I think like at the moment, most of the work, like due to the compute power of it, we have like a lot of the work has shifted towards more experimental methods. Like, however, like typically, like the best methods are actually fairly heavy mathematical as well. Like people. Like you still have to prove that something is an unbiased estimator and has low variance. So both, I would say.
All right. Yeah, thanks. The next one is, Robin is asking how to deal with, POMDP, as you mentioned. Is recurrent networks enough? Sorry, I missed the abbreviation.
It is enough in theory, like if you have a single player. But if you have more than two players, like algorithms like are very different. In practice, it is not necessarily enough. And like there are other algorithms that are designed for multiple players and partial observability. So for example, like counterfactual regret minimization, like would be able to deal with it arguably better than maybe like U-learning. using naively, and there are like versions of very special algorithms that typically were designed for a multi-agent case. However, like recurrent neural networks in theory are enough, but like whether in practice they converge, like it's a separate problem.
All right. Next, Mantas Lukoševičius is asking, is actually like congratulating you. A very nice talk. You mentioned that some kind of simulator of the environment can also be learned, which looks biologically plausible. What about learning a simulation of other agents in the environment?
Oh, so okay. So it is already like in a general case difficult to distinguish what another agent is unless you are told, because this is the non-stationary part of the environment. And even like learning simulation itself is very tricky. Imagine the following thing: you make tiny mistakes. And imagine like you are trying to squeeze through a door in a bus, but the door is just like too narrow. And it may make a very big difference, like if you get stuck in the door. And what happens typically with learned environments, unless you learn them very precisely, and when you use planning algorithms like MCTS on top of them, you can try to squeeze through the gaps that are just too narrow, because you're launching an adversarial attack on your model. So the point is, you can try learn the behavior of your opponents. By the way, but it is difficult, and many reinforcement learning algorithms designed for multi-agent case do that implicitly, not explicitly, but implicitly, like they reason about like what your opponent could be doing. So, but of course, like there is the distinction whether you want to plan based on it and run a tree search, or whether you just want to read off a value function. So like to some extent, like if you would just want to read off a value function, to some extent, like StarCraft would be doing that, but would be doing that implicitly.
Right. Yeah. Thanks for your answer. I think that's all the time that we have today.
Thank you very much.
For everybody else, if you still have questions for Audrūnas, please post them on Slack. And Audrūnas, would be really great if you could join our Eastern European Machine Learning Slack and check out or answer a few questions.
Okay. Thank you. It's been a pleasure. Have a good day.